0.5 molar HCl is used with saturated calcium hydroxide, and the average volume of HCl was 19.45 centimeters cubed. We titrated with 25 centimeters cubed of calcium hydroxide. And so what we mean by titrated with is we balanced, or we reached a chemical balance here. Or in an acid-base question, it's going to be neutrality. So HCl is a strong acid, meaning we get essentially complete dissociation into H3O plus Cl minus. And calcium hydroxide is a strong base, meaning we get effectively complete dissociation into its constituents as well. So in reality, what we have in solution is H3O plus OH minus going to water. Okay, so just because, again, these are complete dissociation products, and so as we can see, these exist in a 1-to-1 ratio here, and so this is what we'll use to solve our problem here, along with these two expressions. So if we have a 0.05 molar HCl, and our volume of HCl is 19.45 centimeters cubed. Okay, so our concentration is our moles over our volume, and so our number of moles is our concentration times our volume, which in this case is 0.05 moles per liter. 0.05 moles per liter times this 19.45 centimeters cubed, and a liter, I should have, I'm going to write my unit conversions down below, just because there's a few of them. So moles per liter times this 19.45 centimeters cubed. So a liter is a decimeter cubed. So there's 1 liter per decimeter cubed, and there's it's a decimeter per 10 centimeters. Yeah, so I should have done it the other way. Yeah, 1 decimeter, per 10 centimeters. Yeah, I should have done it this way. There's a decimeter per 10 centimeters, so that needs to be cubed. Okay, so then that'll give us decimeter cubed over centimeters cubed. These decimeters will cancel these centimeters will cancel these, and this liter will cancel this, leaving us an answer in moles. So that looks good. And when running through it yourself, don't forget the cube, right? So that's 10 cubed or 1,000. And so this works out to, where is my answer? There it is. 9.9 9.725 times 10 to the minus 4 moles. There. Okay. So the number of moles of HCl used is then this. And then from our dissociation up above here, we see that we get complete dissociation. So this is also our number of moles of H3O plus, and it would also be our number of moles of chlorine, right? So then that means that our H3O plus is our number of moles of HCl. And because these two must exist in a 1-to-1 equilibrium in this expression, that must also equal that, right? So the number of moles that we must have titrated to reach neutrality is then equal to that. So our N for our OH minus must be 9.725 times 10 to the minus 4 moles, as the two must equal each other to have reached a neutral solution. And okay, so then the third part of the question asks, so if that's the number of moles, what the concentration of OH minus in the 25 centimeter cube solution of calcium hydroxide was. So the concentration of OH minus is then our moles over our volume, which in this case is 9.725 times 10 to the minus 4 moles over our 25 centimeters cubed. And again, we're going to need to multiply by 10 centimeters per decimeter cubed, and a decimeter cubed is a liter. So that'll cancel these decimeters, this will cancel the centimeters, and we're going to end up with moles per liter, which is what we want. And so if we work this through, we'll get 3.89 times 10 to the minus 2 moles per liter. Okay, and so that's our concentration of OH minus. And then it asks us now to calculate KSP for calcium hydroxide. So I'm just going to rewrite the calcium hydroxide dissociation down here, just so that we have it. Okay, so our KSP, also that's solid, and these are aqueous. So our KSP is just going to be our concentration of calcium 2 plus times our concentration of OH minus squared, because of the 2. We have our concentration of OH minus, but from our balanced equation, we can see that our concentration of calcium 2 plus must be, so our concentration of OH minus will be double that of calcium 2 plus, or our calcium 2 plus will be half that of OH minus. So it should be our concentration of OH minus over 2, which is 3.89 times 10 to the minus 2 over 2, that's molar, or 1.945 times 10 to the minus 2 molar. Okay, and so our KSP is just 1.945 times 10 to the minus 2 times 3.89 times 10 to the minus 2 squared. And if we work this through, it is 2.94 times 10 to the minus 5. And then, so there's our KSP. And so I believe, I believe that's all 3 parts of this question. So you can also write a balanced chemical equation for the whole thing, but HCl and calcium hydroxide do completely dissociate, but you can write it like this. If you do it this way though, as they've found, you calculate your number of moles of HCl, and then you would need to divide by 2 to get your number of moles of calcium hydroxide, but then you would need to multiply by 2 to get your number of moles of OH minus. And so then your number of moles of OH minus still comes out to be 9.725, because your number of moles of OH has to equal your number of moles of H3O plus. Okay, so that looks good. So then for getting the concentration, you divide by your volume, so you get this 0.0389 or 3.89 times 10 to the minus 2, so that looks good. And then for the KSP value, you need your concentration of calcium 2 plus, which is just half, so about 1.0195. So I've got an extra decimal place there, but that's okay. And it turns out that extra decimal place changes that second decimal place value, but again, it's close enough. It's just off by a rounding error, so our KSPs are the same. So that all looks good.